Hi, my name is Jian Wu. I'm from the Sail Drone data team, and today we're going to talk about tracking detected vessels at sea from unmanned surface vehicle. And joining me today is my colleague Mason.
Hi, I'm Mason, also from Sail Drone, also on the data team. So we're going to talk to you about sail drones, which are unmanned surface vessels. But before that, we're going to talk to you about the ocean. Sorry, get these slides working. So the ocean is a large place. You might know this. It covers 70% of our planet. And if you were at the last talk, you were aware that most of it is unexplored. Only 25% of our ocean has been mapped, and you can imagine that what is actively monitored is a small fraction of even that. So we have all these logistical problems with monitoring the ocean, with mapping the ocean, and largely they are a challenge of, since the ocean is so remote, you have to transport people and transport vehicles far out into the ocean. So you have to supply food, you have to supply fuel, and yeah, it creates a lot of unique challenges. In response to that, we have created the sail drone. So the sail drone is an autonomous vessel that is transported by wind power, completely supported by, or generally supported by solar power. And it solves a lot of these problems. You don't have to transport people out there, you don't have to transport food out there, you don't have to transport fuel out there. And so based on this, there's a lot of applications that we've identified and that are useful for this product. Seafloor mapping, which you saw a talk about the challenges associated with that if you were in this room right before. Ocean research, so weather research, animals, all kinds of ocean science applications. And the product that I think is maybe most interesting to this group is defense and security, so maritime domain awareness. This is our real-time ocean monitoring product. So what does that mean? What are the applications of maritime domain awareness? Well, you can think about drug interdiction, you can think about human trafficking, ecosystem monitoring, illegal fishing, things like that. The way we support this is we have a variety of payloads on our sail drone. Radar, PTZ camera, ML models, enabled real-time detection and alerting based on those camera images, passive acoustics, and an automated identification system transceiver. So using all of that, we have built a data platform on top of that to process that data and do real-time alerting. And I'll let Jen speak to that.
Thanks, Mason. We've introduced the capability of the MDA product. Here is an overview of the MDA system, focusing on where the data is collected all the way to where the data is displayed. So we've deployed a fleet of drones onto the ocean, literally can be deployed anywhere in the world. And the data out there, like collecting, the drone out there collecting the data 24/7, and data is transmitted via satellite all the way to our cloud infrastructure, which is powered by Postgres and PostGIS. And using them really allow us to, like managing geospatial data efficiently in terms of rapid storage, indexing, and the querying of large data sets. And another thing our cloud infrastructure is doing is to process the data. So the processed data is fed directly into the user interface known as Mission Portal. And Mission Portal is a web security application that provides user data in real time. And you can view the data on your laptop, and you can view the data on your cell phone. And again, drone can be deployed anywhere in the world, and you can view the data anywhere in the world, because this is very important to the customer, because we have we have an international customer all over the place, and very important for us because we have pilots, we have mission managers working in different time zones across the world. MDA system is composed of a few subsystems. We're going to go over one by one, starting with the sensor detection at the edge. Cell drone is usually equipped with a wide array of sensors. Here we just highlight the most important or the most critical ones to enable us to do the MDA functionality. At the bottom of the drone, we have INS, inertial navigation system providing the drone position data. We have AIS transceiver in the middle, receiving the AIS signals from the surrounding vessels, providing the vessel metadata, such as vessel identification, where it's coming from and where it's heading to. And at the top, we have a radar and, of course, our ML-based camera system. Radar just scanning the surroundings by sending out the radar waves, and camera system that's constantly taking pictures and identify what's in the pictures. So, think about this, and each of the sensors is collecting data, and all this raw data kind of very noisy and inconsistent. So we do have some onboard data processing to sort of understand this raw data and correlate them and trying to fuse them together in order to generate coherent tracks. So we do have this, we call it a tracker, and later we apply some smoothing algorithms to make it much better looking trajectories. So with that, I will hand it over to Mason to talk about what trajectory look like in practice.
Thanks, Jen. So as this is a data conference and we're presenting a real-time product, we're trying to go into some details on how we actually accomplish this. So one of the innovations we had, we're trying to keep this data as up-to-date as possible. So we could send every new data point as it arrives, or we could send all the new data points for every boat all at the same time, but we've adopted a slightly different approach. So we're sending the last segment of the trajectory per vessel for each update that we make from the drone. So what this accomplishes is basically we're batching by contact. So since we're generally writing to the database by contact, we're minimizing database writes, minimizing recalculation. So this is kind of a strategy that we had to employ to do this as a real-time product, which is unique on our offerings. So I'll go back to Jen sorry, this is you? This is you, yes.
Well, when ingesting detections or from the trajectories or from the incremental updates, as Mason mentioned earlier, we, of course, could ingest all of them into the system. But at the end of the day, what really matters is the subset of the data that provides us the meaningful movements of the vessel. So we do a few things. Hopefully you can see the green dots and the red dots on the map. The green dots represent informative detection, and you can see the camera icon, and it is associated with one of the green dots. That means the detection is captured by ML camera. So we prioritize that because the image usually is very intuitive and provides more insights. On the top of that, we focusing on movements where significant changes happens in terms of speed over ground or course over ground, make it simpler to understand. So for instance, a vessel speeds up or slows down, or make a sudden shift in directions. Those moments or those events are worth highlighting because that sometimes indicates something might be happening in its environments. So in contrast, the green dot represents the less interest data points. You can imagine you are out on the ocean and you saw a beautiful yacht. It might look very stunning against the horizon. It might be very appealing to you, but actually it's very boring to us because it's been anchored there forever not forever, like in the past 2 hours, and doesn't move at all. So we unfortunately have to downsample it. That's an extreme case, but the vessel may be still moving, but doesn't like move that much. So we remain some of the data points in its trajectory and downsample some red dots in order to like not overwhelm the system. So by focusing on all these factors, we ensure that we always display the most relevant, the most actionable data onto our user interface.
Good.
By now, I think we've talked about how we process the data on board. We've already talked about how the data of the board look like, and we've talked about how we ingest data. I want to turn the attention to our cloud service. Again, this is backed by Postgres and PostGS. Here is the problem. 3 drones shown here, just an representation, but think about we deploy like more than 3 drones. We deploy 10 drones into a mission, and more or less at the same time, 10 drones detect the same vessel, and they all like start sending us the 10 different reports back to our cloud service. That creates a challenge, because how do we ensure that 10 different drones actually describing the same vessel? So our backend service essentially is multi-drone, multi-sensor fusing data processing. It's trying to like understand all these 10 different reports and generate a unified story of the same vessel. And also like sometimes one drone may be very close to this detected vessel, and some other drones receive better signals describing like speed or crossover grounds. So this backend service take all these inputs into account, and we're trying to like understand it better and always generate accurate information about like what's really happening on the ocean.
Thank you, Jen. So as we've kind of hinted at, this is our data model. We have kind of a metadata table for contacts, for vessel metadata. And then we have a one-to-many relationship down to our detections table. So this contains detection data, but it also contains all of our post-GIS data, our location data. So this is where the geo magic kind of happens. So all of our indexing in terms of geospatial data is happening on the detections table. And you can see that this kind of fits into that right paradigm that we were talking about earlier, where one vessel's data comes in at one time. And so that's one update to the contacts table, and then many updates to the detection table grouped by that vessel ID. And so then what do we get out of this? Well, here's a view of our real-time data platform. You can think about this as kind of like a mall security camera for the ocean. So what are we seeing in real time? Here it is all right here. And as you can see, San Francisco Bay, it's a very busy area. And so this is kind of a messy, noisy view. So there's lots of vessels out there doing lots of things. How do we sift through this data? Well, we've got all this object metadata, all this detections metadata, and based on that, we can do real-time filtering. So this is something that your mall security cameras don't have. We can take away objects that are not currently moving. So in this case, we filtered out vessels that have an average speed of ground of less than 6 knots. So every vessel here is active, and so we get a real-time view of not only all vessels, but all vessels that are actually doing something. Let's suppose we wanted a different roll-up of that data. We have a playback mode. So give me a 2-hour chunk. Here's all the vessels that are moving during this 2-hour chunk. Again, we filtered on 6 knots. And here's their entire tracks. And not only that, we can scroll through these tracks, providing a real-time or a playback mode of these vessels. And let's say there's a highly suspicious vehicle that we really want to zoom in on. We can look at the contact details, so it displays all the vessel metadata, but also every single point has its own metadata. Every single detection is located on this timeline. This is the entire history of the vessel, where it went, how fast it was traveling, which direction it was headed, and what sensor modalities we saw it with. Another feature that I think will be of particular interest to PostGIS folks is we have notifications and saved filters. So this is kind of a tricky problem. We have lots and lots of boats, lots of trajectories, lots of detections coming in every second, and we also might have tons of customers with lots of different filters. So in our previous views, we had one filter generated by one customer at a single time, and so you think about that as a query against the metadata in our database. In this case, if we wanted to run one filter per one query per filter, we might have 10,000 filters saved in our filters table. How do we run 10,000 queries every time we get a new data point? Hundreds of data points per second, maybe. Well, we've inverted this problem, and so we're not actually querying the trajectories, we're querying the filters table against the trajectories report. And so the nice thing about ST-intersects and various other PostGIS operations is that they're symmetric. So if the trajectories intersect a bounding box, so like an area you're particularly interested in filtering on, that's the same as the bounding box intersecting the track. So yeah, this is how we've managed to support kind of otherwise what would be a lot of different comparisons all at once. I'll let Jen speak to heat maps.
By now, you probably remember, like we mentioned multiple times, like we have primarily we'll have two tables, and one table containing the vessel level like metadata, and the other one is a geo-index detection data we collect. And we get all this data, and the user can view them in real time and even get notified in real time. And you also can use the playback mode or the historical mode to view data and what else we can do with it. So with this historical data, we can do some advanced analysis and the data visualization. Heat map is just one of the things we've done for our customer. In this case, we filter the data based on a few filter criteria, things like time range, let's say like past 2 months, and area of interest. Here is San Francisco Harbor again, because that's where we are from, and the type of vessel. So that would result in a heat map on the right. This visualization tool is very powerful and very intuitive, and user can have this and make informed decisions based on the like long-term vessel activities and the patterns and trends, and they can based on that they can make like actionable steps based on the information we provide.
Thank you. Another application of kind of our offline analytical processing is ML labeling. So if you've ever trained an image model, you might be aware that one of the most difficult tasks is actually generating the data set. And so how do we train a data set on the images that our boat collects? So first we had to generate a suitable set of images to train our model on. So one way we informed this was using the USGS coastline data set, which was just spoken about in the last topic. So we tag the images with using our location data and the camera metadata, and also the position. We try to figure out which images are likely to contain a coastline in the background that will confuse the image model. And so we found a bunch of open water images and used those to identify boats. And so now we've got a high quality data set that's good at recognizing boat, not boat. And so we can actually apply this when we're closer to the coastline. So this was kind of a nice application of geographical data, merging data sets to help us wade through this process of generating a data set. Other data sets that we've used, these image data sets, we've also generated ML models for vessel length and vessel classification. What type of boat is it? Is it commercial boat? Is it a pleasure craft? Things like that. So that's of high interest to our customers. So it's nice to be able to pull in these external data sources on data that we've been collecting in real time, and then later get extra added value out of those. So that's our MDA product. Hopefully SailDrone has been interesting, and maybe, I don't know, if you're trying to build real-time data pipelines, then maybe some things have been of particular interest. If you really like our company, then we are hiring, and so yeah, feel free to reach out, and maybe you'll join us someday. And we're free for questions if there are some. Yes?
So you're describing about the data pull for your detection. How about the cell drones themselves? Are you actually tracking keeping track of their duration as it's leveraging the sake of space? Are you doing something all with it? As what are you backing up to the ML spot of it? Are you turning around and using that and tasking of the drones themselves in terms of like where they might direct to that could be?
For the first question, yes, our detection metadata does include the position of the sail drone. So yeah, we have ranged a vessel, we have sail drone position, we have target.
I'm more the sail drone itself. It's up so like how you have the metadata on each ship, and you have that contact issues where like the sail drone itself is going to have its own metadata.
So that trajectory of the sail drone is tacked on to the contact trajectory. So yeah, it's present. That's how we get it back. They're all passed in this trajectory report. So in terms of your second question, some of the heat maps that we showed, it's kind of human generated at this point. Like where might we be of most interest? If that speaks to your question. It is a thought that an ML model might kind of strategically distribute our sail drones more efficiently. We're not there yet, but it is an active thought that we've been looking into. Yeah. Yes.
In terms of object detection, you guys thinking about expanding things beyond boats. So I'm thinking cargo vessels, when there's big storm to sea and lots of containers are blown off, or things like Fukushima, the big Fukushima earthquake that generated a lot of floating debris, including docks and shipping containers and things like that, or I don't know, large blocks of seabird. I don't know, various things that you might see that would be floating on the surface of the water that would be large, but it wouldn't necessarily be a ship.
So I think the flotsam and jetsam idea, that's a great application, like in terms of how polluted is the ocean. I don't know that we've actually thought about that. We have thought about other means of detection. There's a partnership we've had with Now RDC. They're trying to generate a good ways to detect marine mammals, and also good laws on how to protect marine mammals from construction and boats and things like that. And so we've been working with them on what's the best way to use our product and to detect marine mammals. So another thing that comes to mind is a lot of our ocean science products, we're just plugging sensors into the water. So when you mentioned Fukushima, if you were trying to measure ocean pollution, I'm sure we could easily plug in a radiation detector or cesium detector or something like that. So I think the large debris question is interesting. I don't think we thought about that, but there are other things that we have kind of explored in our space. Yeah. Yes.
So the worst sea condition that you still can navigate at this.
Navigation and survive are two different things. We have hurricane drones. So we partner with NOAA, and we put out sail drones. There's some in the Caribbean right now. I don't think any are actively engaged with the current tropical storm off the coast of Texas, Louisiana, but we're off the coast of Florida, out in the Atlantic, waiting on hurricanes. And so I don't know the exact number, but I believe we've survived sustained winds over 100 miles per hour. But At that point, we're not navigating. We're trying to position ourselves in front of the storm, trying our best to get to where the eye is going to go, and then we're at a whim for the sea, with the sea for the next 36 hours. But we've used this to record surface ocean data inside the eye wall of a storm, which has never been done before for Saildrone. So, yeah. Yes.
So you mentioned AIS on Saildrone. Are you pulling the AIS signatures from the other vessels and identifying those that have AIS versus non-AIS?
Yes, 100%. Yeah. So, yeah, we call the non-AIS vessels dark targets, and so kind of using AIS to calibrate our sensors, but then, yeah, a big portion of what we offer is identifying dark targets, and yeah. Any further questions? Well, thank you all, and we're happy to talk after this. There's a nice break, so enjoy yourselves.